We stand at the edge of a technological revolution: quantum computing. This is a moment in history where the boundaries of what's possible are being redrawn, and the very foundations of computation are being reimagined before our eyes. For decades, classical computers powered our world, solving problems from sending rockets to the moon to connecting billions of people online. Yet, despite their incredible speed and power, some challenges, like simulating molecules or breaking complex codes, remain far beyond their reach. Enter quantum computers, machines that harness the strange and counterintuitive rules of quantum mechanics. They don't just process information, they unlock entirely new ways of thinking about data and computation. Unlike classical bits, quantum bits, or qubits, can exist in multiple states at once, exploring many possibilities simultaneously. This unique property gives quantum computers the potential to solve problems that would take classical machines millions of years. This is not just an upgrade, it's a complete reimagining of computation itself. Quantum computers represent a leap as significant as the jump from the abacus to the supercomputer. Imagine a maze. While a classical computer tries every path one by one, a quantum computer explores all possible routes at the same time, finding solutions with unprecedented speed and efficiency. Building these machines is a feat of engineering, requiring temperatures colder than deep space and shielding from even the tiniest vibrations or electromagnetic noise. Every detail must be meticulously controlled. In this journey, we'll demystify qubits, entanglement, and the engineering marvels behind quantum hardware. We'll explore the science, the challenges, and the breakthroughs that are making quantum computing a reality. We'll meet the pioneers, visionary scientists and engineers who are turning theory into reality, pushing the boundaries of what technology can achieve. Welcome to the birth of a new era, where quantum hardware could change our world in ways we're only beginning to imagine. The future of computing starts now, and its possibilities are as vast as our curiosity. To understand quantum computers, meet their core, the qubit. These tiny units are the building blocks of quantum information, much like classical bits are for traditional computers. Classical bits are simple, either 0 or 1. They form the basis of all classical computing, processing information in a straightforward binary manner. Qubits, however, use superposition, existing as 0, 1, or both at once. This unique property allows them to perform multiple calculations simultaneously, vastly increasing computational power. Picture a spinning coin. While in the air, it's both heads and tails. Only when it lands do you see the result. This is similar to how qubits behave in superposition. Qubits remain in this fuzzy state until measured. This uncertainty is what gives quantum computers their unique edge. But there's more: entanglement. When qubits are entangled, their states are linked no matter the distance. This means changes to one qubit instantly affect the other. Measure one, and you instantly know the other's state. This phenomenon is what Einstein famously referred to as spooky action at a distance. This combination of superposition and entanglement gives quantum computers their exponential power. It allows them to solve complex problems much faster than classical computers. 2 classical bits represent one of 4 combinations at a time. 2 qubits can represent all 4 simultaneously. This parallelism is a key advantage of quantum computing. Add more qubits and the possibilities explode. The computational power grows exponentially, enabling tasks that were previously unimaginable. With just 300 qubits, a quantum computer could, in theory, process more states than atoms in the universe. This illustrates the immense potential of quantum computing. This is the scaling power classical computers can't match. Quantum computers can handle vast amounts of data and complex calculations with ease. It's the foundation of quantum advantage. As we continue to develop this technology, the possibilities for innovation and discovery are boundless. Creating and controlling qubits is a monumental challenge. Qubits are fragile. Tiny disturbances can destroy their quantum state, a process called decoherence. To protect them, quantum computers operate at temperatures near absolute zero, colder than outer space. This is achieved with dilution refrigerators, cooling the processor over several days. The quantum chip, often fingernail-sized, is shielded from electromagnetic interference by layers of special materials. Inside this ultra-cold, shielded chamber, qubits can perform calculations before decohering. Qubits can be made from superconducting circuits or trapped ions, each with unique strengths and weaknesses. Superconducting qubits are fast but less stable. Trapped ions are stable but slower. Scientists worldwide are racing to build the perfect stable qubit. The quest for robust quantum hardware is a global effort. A real quantum computer looks nothing like a laptop. Instead, you'll see a large cylindrical canister, the dilution refrigerator, suspended in a frame surrounded by electronics. Hanging inside is a complex chandelier-like structure. At the top are control electronics, generating precise microwave pulses to manipulate qubits. Special coaxial cables carry signals down through progressively colder plates, each stage shielding and cooling further. Gold-plated components ensure reliable connections at cryogenic temperatures. At the very bottom, in the coldest region, sits the quantum processor chip. Here, qubits are manipulated and entangled, running quantum algorithms. Results travel back up to the classical electronics for interpretation. Quantum hardware needs software to unlock its power. Quantum software translates human instructions into precise signals for qubits. Tools like IBM's Qiskit let anyone program quantum computers using Python. Users design quantum circuits, flowcharts for qubits, by arranging quantum gates. These programs can run on simulators or real quantum hardware via the cloud. This accessibility has democratized quantum computing, creating a global community of developers. Quantum software also optimizes programs for today's noisy, imperfect hardware. Current machines, called NISQ devices, require clever software to get reliable results. The partnership between software and hardware is pushing the boundaries of what's possible. It's a new era of collaborative discovery. The biggest obstacle to practical quantum computers is errors. Qubits are sensitive. Decoherence and control imperfections introduce mistakes. These errors accumulate, limiting what today's machines can solve. Quantum error correction is the solution, but it's far from simple. Unlike classical bits, qubits can't be copied due to the no-cloning theorem. Instead, information is spread across many entangled physical qubits to protect a single logical qubit. Special circuits detect and correct errors without destroying the quantum information. Building a fault-tolerant quantum computer may require thousands of physical qubits for each logical one. Today's processors have only a few hundred, but progress is rapid. Mastering error correction is the holy grail of quantum hardware. Why build quantum computers? To solve problems classical machines can't. Simulating nature, molecules, proteins, materials is nearly impossible for classical computers. Quantum computers could revolutionize drug discovery, modeling molecular interactions for new medicines. They could design advanced materials like better catalysts or superconductors, atom by atom. In agriculture, quantum-designed catalysts could make fertilizer production far more efficient. Quantum algorithms also promise breakthroughs in optimization, logistics, finance, and AI. Problems with countless combinations like delivery routes or investment portfolios could be solved faster and better. Quantum computing could transform entire industries. The world is in a quantum race, nations and corporations vying for quantum advantage. Governments are investing billions in research, infrastructure, and workforce training. The US, China, EU, UK, and others are building national quantum programs. Tech giants like Google, IBM, and Microsoft compete to build better quantum processors. Startups are innovating in software, hardware, and control systems. Competition drives rapid progress, but collaboration is vital. Researchers share breakthroughs in journals and conferences. Open-source tools like Qiskit unite the global community. This blend of rivalry and teamwork is accelerating the quantum revolution. Behind every quantum breakthrough is a human story, a tapestry woven from countless dreams, setbacks, and triumphs. Each discovery is not just a leap in science, but a testament to the people who dared to ask, what if? The journey began with pioneers like Planck, Einstein, and Schrödinger, whose bold theories laid the foundation for a new understanding of reality. Their curiosity and courage opened doors to worlds no one had imagined before. Today's scientists and engineers labor in labs around the globe, pushing the limits of what's possible. They collaborate across continents, sharing ideas and building on each other's work, united by a common goal. Progress is measured in tiny steps, lower error rates, longer coherence times, and new ways to control fragile quantum states. Each small victory brings us closer to unlocking the full potential of quantum technology. Students and enthusiasts worldwide now write quantum programs thanks to open access and cloud tools. The next generation is learning, experimenting, and contributing, making quantum science more accessible than ever. The field is more diverse and interdisciplinary than ever, drawing talent from physics, chemistry, engineering, and even computer science. Collaboration across backgrounds sparks new ideas and accelerates progress. Quantum research is driven by curiosity, imagination, and the desire to solve humanity's biggest challenges. Every equation written and every experiment run is fueled by hope for a better future. These dreamers and builders are the true energy behind the quantum age. Their passion and perseverance turn abstract theory into real-world innovation. They stand on the shoulders of giants, honoring the past while paving the way for future generations. Each new insight is a bridge between what was and what could be. The quantum revolution is, above all, a human endeavor, an ongoing story of curiosity, collaboration, and the relentless pursuit of knowledge.